Yeah. All right, so ladies and gentlemen, what we're going to work on today is we're going to be working on what's called the central limit theorem. Okay. That is not the first page. Sorry about that. I thought it was. That's the first page. I apologize. You're going to need that. But this one, hey, guys, just take a look. I don't know if you need to write this stuff down. Okay? More of what this is just information for what we're going to go over this chapter. Okay? So, central limit theorem. Okay? Things that we're going to talk about this chapter. I'm going to try and get this out in front of you a little bit more often so you kind of know what's coming here. All right? We're going to recognize, first of all, central limit theorem problems. Okay? How do you figure that out? That is one of the issues that we've had over the last few chapters is, all right, which one is this? Okay, we got to figure that out. So we're going to talk about that. We're going to classify continuous word problems by their distributions. That's part of that first one. Okay, and the big things from this chapter are the central limit theorem for means, so the averages, and for the sums. Okay, and that central limit theorem for means is what we're going to talk about today. Okay, now that bottom part down there is very, very important. Okay, central limit theorem is, first of all, one of the most powerful and useful ideas in all of statistics. It is used more than anything else. Okay, if you think back to, and I'm going to show you in just a second here, if you think back to anything statistics-wise that you were taught in Algebra 2 and in College Algebra and Pre-Calc, we were mainly talking about normal distributions. Okay, all right. In fact, that's what we did yesterday in Algebra 2, and I'll just show you really quick what they did here. Okay, so all right, in my hands here I have part of a deck of cards. I didn't pull the whole deck because of what we're trying to do here. All right, so I pulled the cards that were ace through 6, okay, from each one of the students. And then I had each one of the kids take 2 cards, okay? So you take any 2 cards that you wanted, okay? I'll let everybody choose. You add them together, and we tally them up here, okay? So what should happen is if you do it enough, what should happen? Okay, which one of those numbers there do you think should be pulled the most often? Why?
Because it has the most combinations.
Right, it has the most combinations. Okay, 1 and 6, 2 and 5, and so on. Right. Okay, which one should be pulled the least amount? 2 and 12. Right. 2 you can only get if you pull 2 aces. 12 is only if you pull 2 sixes. Right. Okay. Now you can see that didn't really happen, right? We even tried to draw what the graph of this was, and it didn't work out because it ended up looking like that graph right there, okay? Now, the reason why it looked that way was I only had 14 kids in class yesterday. Is 14 kids enough to be able to get a good, for example, bell curve? You should have a bell curve if you do this enough. No. I mean, in fact, for our 2, we had more 2s than we had 10s. If you look back at this, okay? We had more 2s and 3s than we had 10s. We had the same number of 2s as we had 9s. Now that should not happen, but when you do a sample, it can happen, okay? Now, one of the reasons why we didn't get that bell curve was, sorry, that's next time, is this bottom part, okay? You have to have a large enough sample size. What is large enough? Well, you kind of have to do it enough to be able to start to see what's going to happen here, all right? Many times, the central limit theorem gets used with too small of a sample size, okay? You have to have a large enough sample size to be able to do this. An example of when this was used improperly, okay? My wife told me about this, so I get to use her story, all right? She was working, this was quite a few years ago, and they were trying to, anytime you go into the doctor, they have to fill out charts on you and all this paperwork and everything. And it's got to be filled out properly to be able to make sure that everything is taken care of and they're meeting all their regulations and everything. Okay, so my wife was routinely seeing about 100 patients a week. Okay, so in a month, we're talking, she was really close to about 500 a month. Okay, in a month, they were trying to figure out if she was doing her charts properly by pulling 4 charts. 4 random charts in a month, and they're like, well, if you got all 4 of those right, that's good enough. You guys know well enough with doing homework that sometimes, especially with me spot checking your stuff, sometimes it's a game of Russian roulette, isn't it? Okay. Yeah. Is he necessarily going to catch that I just copied down the answer this time?
Yeah.
Depends on if you copy the whole thing, right? Okay. But say you come across a question where you're like, I don't know how to do it. And I don't want to spend the time to figure it out. I'm just going to copy down what it says and I'm going to move on. Because you guys have never done that, right? Never. Okay. Now, same thing in this situation. 4 out of 500. And she got dinged on it quite often because she would normally have one of them where she missed something. So she missed one thing out of 4 charts.
Mr. Doctor?
Yes. Yeah?
Could you dismiss Autumn Kramer?
Yep.
Thanks.
All right. 1 out of 4 charts, she missed one thing off. Does that mean that she wasn't doing that part of her job well? Well, honestly, we don't know because they only pulled 4 charts. Okay. As it says down there, sample size, to get a good idea of what's going on, you need to have a minimum of at least 30 of whatever we're doing. Okay. So if we go back to that chart that I showed you with the Algebra 2 kids, one reason why we didn't get a bell curve was I only had 14 kids pull. Okay. If I were to continue to pull, okay, maybe I get it to be closer. Okay. I just pulled 2 cards. There's an 8. Okay. And you continue to do that until you get something that's a little bit more expected. And that's what the central limit theorem is talking about. Okay, so big part. When you're doing this, you have to have a sample size that is large enough to get good data from. Okay, when we're doing stuff in class, the sample size is going to be big enough. Okay, so then how do we handle this stuff? That's what we're going to talk about next. Okay, so we're going to start, like I said, by talking about the central limit theorem for finding sample means. Okay, and as you guys know, the mean means the average. Yeah, we're going to pick on Eli a little bit here.
We didn't have a running back this year.
I'm not going to comment on that.
Didn't say very.
We could also pick on Max, but I don't remember very many throws where he went backwards. So, and most of his throws were well over 2 yards, right, Max?
Yeah.
Yeah. So we'll pick on Eli instead. Okay, Eli, you're gonna be a good sport. Let me pick on you a little bit. No. Can we pretend it's Trey then?
Yeah.
Or would Trey have just better numbers than this? Good point. Good point. Well, that'd be a negative then, wouldn't it? Come on now. What? All right. So we're going to suppose we have a running back here for our football team, we'll, Trey or Eli, I don't care, it doesn't matter, okay? Eli, should we just pick on Trey? Okay, so Trey started the game. He got 5 carries right away. We could figure out what his average is. How do you find the average of those numbers? Add them up, divide by 5, right? Okay, so what's going to happen there? We add those up. We end up with, what is that? 23 divided by 5, I believe it is what is that? 4.6. Thank you. So he's starting after those 5 carries. He's starting with a 4.6 yards per carry, right? Okay. After that, now if that's only, those are only Trey's 5 carries that he got for the whole game, well, then we're done, right? But for some reason, Max just decides to keep giving Trey the ball. Okay, so his next time, well, he gets another carry. This time he gets it for 8. Okay, does his average per carry change? Yeah, it's going to change, and it's going to change continuously every time he touches the ball. Okay, Max decides to pitch him the ball. Max pitches the ball well behind him. Trey picks it up. He gets -12. Okay. They decide to do it again. Okay. Trey fumbles the ball. Then he decides to go backwards, and Trey's going to really like this lesson. All right. We're picking on the boy, and he's not even here. Okay. But what's going on here, guys, is with every carry, the average isn't 4.6 anymore, is it? The average is constantly changing, okay? So how do we deal with that when the average is constantly changing? That's the concept that we're going to talk about today. And that's what this is saying down here below, okay? When the sample size changes, we added to the sample size. Then the mean and the standard deviation are also going to change. We didn't talk about standard deviation, but you guys know from our equations that those are going to change also. Okay, how we're going to denote that when those are constantly changing is we're going to denote it by our mu of x for the mean, and then we've got this for our standard deviation. Okay, so a normal distribution equation, or how it gets set up, looks like x as it, I don't even know what this stands for, but this is talking about a normal distribution. And then we've got 2 numbers, just like we did before for our normal distribution. Our first one was our average. Our second one was our standard deviation. Now our standard deviation changes. Okay, so I couldn't make the parentheses big enough to make sure that this was all in there. But our standard deviation, we're going to take our standard deviation number and then divide by the square root of how big our sample size is. Okay, so I'm going to show you how we do that in just a little bit here. Just the standard deviation is divided by that. All right, the first number is still your average of your sample set. Okay. All right, any questions so far? All right, so because of that though, finding our z-score is also going to change. Remember our z-score equation was whatever our number is minus our average or our mean divided by standard deviation. Okay, that is still the same equation, but we had to adjust the standard deviation because our sample size is changing. Okay, just notice that this is still talking about what we talked about on the last page. Okay, x, so our number, minus our average divided by, and this is how we're going to find our standard deviation when that is constantly changing. All right, so we're going to go through and we're going to solve some different things based on that. Okay, do I need to go back? I'm sorry. I thought I was fast enough. Or slow enough. You said it, not me. All right, so here's a couple problems that you guys could be asked in the homework dealing with what we're talking about here, okay? We have an unknown distribution that has an average of 90 and a standard deviation of 15. The sample size is n equals 25 and is drawn randomly from the population. We want to find the probability that the sample size is between 85 and 92. Now, you will need your calculator for this. So once you get it written down, make sure your calculator's out so we can figure out the exact value here. All right, so one way to start this, and you're going to be asked to do this every once in a while, okay? You're going to be asked to draw out the situation, okay? Draw it out on a graph. All right, now with what we're talking about here, this is going to be on a bell curve. Okay, so we draw in that shape there. Okay, now what we know for sure, we know the middle line is our what?
Mean.
Yep, it's our mean, it's our average, okay? Do you realize also that what is also going to be that middle line here when it's normally distributed? Our mean and our median are going to be the same for these. Okay, so that's our first part there. Okay, we draw in the mean, and then what this is talking about, we could put our standard deviation in there, but it doesn't really apply to this, so we don't need to. But what we can do from there is we can draw in, we want to find what's the probability that the sample mean is between 85 and 92. So we are trying to find the area on this side and the area on this side. Okay, so we've done these problems. We just got to change it just a little bit here. Okay, so if you go into your calculator, you go to your, now is this going to be a PDF or a CDF situation? This is going to be a CDF because we're looking for in between two values, right? So if you go to your distribution part, we're going to do the normal CDF, okay? And remember in your calculator, you got to put in 4 things, okay? Those 4 things are lower, upper, our mu, and our standard deviation. Well, what do we put in for each one of those? Our lower value is going to be what? 85. It's just going to be our smallest number there. Our upper value is going to be 92. Okay. Our mu for this one is going to be what? 90. Yeah, they already tell it to us. So that's going to be on 90. And then our sample standard deviation, this is the one that switches a little bit. Okay. This is going to be our standard deviation, so 15 divided by the square root of our sample. Okay, now in your calculators, you can just type in that whole thing if you wanted to. Okay, it'll take care of it. It's not a big deal. Okay, if you have to be that person that has to simplify this down, square root of 25, you guys know is 5. 15 divided by 5 is 3. You can also put a 3 in there. You're going to get the exact same value here. Okay, so go ahead and plug those in and let me know what you get here. What's that? A minimum of, what do you mean a minimum of 30? Okay, remember how I said large enough and I put it in quotation marks? Okay, for whatever this situation is, they are saying that this sample size of 25 is large enough. Okay, so when we're doing this for homework and stuff like that in here, we're going to assume that it's large enough. Okay, in the real world, like I said with that example, you got to find a number that is truly large enough so you can trust the information that you're getting. Okay, that makes sense? Did you guys hear what Abigail said? She asked, because if you go back to this first page here, she said sample size needs to be a minimum of 30. Okay, if you look at our problem there, our sample size is not 30, is it? It's 25. But really, what's going on here is it needs to be large enough for your situation. Okay, in your homework, on your test and stuff like that, if they give you a sample size, we're going to assume that it's going to be large enough to be able to pull good data from this. Okay, but in the real world, you've got to have a sample size that is big enough to be able to get information that we can use here. All right, what percentage do we get here?
69.97.
69.97%, right? Okay, and that's all you're doing for this. Okay, so the equation changes a little bit based on how big the sample size is. Okay, all right, now down below, we're going to do something just a touch different, right? Okay, this one says find the value that is 2 standard deviations above the expected value, the 90, which is our average. Okay, so remember what we normally do to find the value that's 2 standard deviations above. Well, we can take our average, so our 90, and then go to plus or 2 times our standard deviation. Okay, but because of our sample size has changed, we have to put that extra part into that. So we are not just dividing by the standard deviation, we are dividing by the square root of our sample size. So for this is going to be 90 plus 2 times standard deviation was 15 divided by the square root of our sample size. So that ends up being 96. Okay. All right. So when do we use this compared to what we did before? When they're telling us how big the sample size is. Yeah, that's exactly right. Okay. All right. Questions at all so far? We good to go on here? No? Abigail, there's a lot of excess noise right in front of her. Yeah, your excess is what I was just saying. All right. Okay, another situation. Okay, the length of time it takes an over 40 group of people to play one soccer match is normally distributed. Okay, and so this is an important part here. With a mean of 2 and standard deviation of 0.5. Sample size, they're telling us, is n equals 50, is drawn randomly from the population. We have to figure out what the sample mean is, or find the probability the sample mean is going to be between 1.8 and 2.3. Okay, so first of all, we can set that up. We can go x, and then we've got our normal distribution. What number goes first here? The mean goes first, okay? We don't have to divide anything by it. That just ends up being a 2 there, okay? Our second number is how we adjust the standard deviation, right? So our standard deviation is 0.5, but then how do we adjust that? Over the square root of 50, okay? And this one we can just leave it that way as you type it in, all right? Now, let's say that they ask for a graph also. We're going to draw on our bell curve. We put in our mean. Our mean was 2. What we want to find for this situation is we want to find it between 1.8 and 2.3. And we want to find all that area in between there. All right, so this one ends up being very similar to the last one, doesn't it? This is a normal CDF, okay, because we're trying to find the area in between those. All right, we've got our lower limit first. Our lower is going to be 1.8. Our upper is 2.3. Our average is 2. And then our standard deviation is 0.5 divided by square root of 50. Okay. Now, what this is saying here, guys, more than anything else, and I know I haven't made a big deal about it so far because I didn't know that I should make a big deal about it. But if you get this part set up that I put in the box here, that's giving you, along with what's in the problem there, that's giving you everything you need to type into your calculator. All right, so what do we get? The probability that is between 1.8 and 2.3 hours. This one's going to be really big. 99.7, yep. All right, so what is this saying? Just about all games are going to fall in between 1.8 and 2.3 hours, right? Okay. Any questions so far? Yes, Abigail. It has to do with the standard deviation, yeah. And unless you figure out that 0.5 divided by a square root of 50 is 0.07, since that is really small, even though these numbers are technically really close to our average, you would think that this would be a small number because they're so close, but because our standard deviation is so small, that's why it's so much, or such a high percentage, okay? Now, if, say we figure this out, and our standard deviation is 0.2, for example, okay, but we know for one standard deviation below and above is approximately 68%, right? Okay, it would be a little bit more than 68% then, okay, if it were a 0.2. Because it's 0.7, it's so much smaller than the rest of it, it's going to be just about all of them, okay? Abigail, good question. All right, any other questions that make me think that I didn't think I was going to have to answer? Because, all right, anything else, guys? What? Nothing. All right, copy this one down. All 4 parts, we're going to put everything that we did together here. Let's go, gentlemen. In fact, as you guys write this down, I want you guys to try this one. And we'll do it afterwards. B might be a little bit harder to figure out because we haven't talked about it enough yet. But we'll talk about it. Get it all down. You should be able to get A and C for sure. We've done D in the past. What did you tell me earlier? How do we know that it's what we did last chapter compared to what we're doing now? We have a sample size, right? Tell me this way I'll put up with this for the last one.
This is all just screwed by on that thing. So we'll get support.
Makes sense? No.
It could be like when you were.
Makes sense?
Once you take that out, oh, I got 100.
All right, we're almost done. We get them figured out, guys?
Wait, hold on. Down? Yeah, let's see. Oh, yeah, yeah.
The sample more than 30. Oh, 30.
I'm not done writing them.
That's why I have to.
30, 60.
And it has to do with the sample size. If you do a sample size that's large enough, you can assume that it's normal distribution, okay? And that's why I had to for this one. Is our sample size large enough?
Oh, we got area.
One of them above 30, then because we have a normal distribution.
Good, because I didn't want to stay in my house, I just said that to be nice. Why not? Well, first you said.
All right, ladies and gentlemen, what about letter A? We get letter A?
Yeah.
What is our mean?
34.
34, right? It tells us, okay? What is the standard deviation here? 15 over the square root of 100, better known as 15 over 10, which is?
Do we have to?
No, you don't have to, but a lot of you are going to. All right. So really, you're not just going to type it all in your calculator?
What you guys get?
Okay, that's fine. All right, so for letter A, we get 34 and 15. Now, what does this distribution look like? Remember, we have talked about different ones. We've talked about uniform distribution. That's where there's a box there. We have talked about exponential distribution. Okay, and we've talked about normal distribution. Okay, there is one key sentence up here that tells you which one it is. What is that key sentence? Yes, yeah, it's this one. Because of our sample size, that tells us it's going to be a normal distribution. And if they ask why? Because, yeah, I don't know why the book wrote it that way. And I wasn't, I don't know anymore. I was a little tired when I was doing this. Because the sample size is 100. All right. Any questions there, gentlemen? Letter C. What do we got for letter C? 99.62. You sure, Eli? That's what I got too. All right. Remember, for your stuff that you're throwing in the calculator, we've got, now, this one's a little bit different, right? Because it says more than 30 years. So if we draw out that graph, okay, we're going to have our average of 34. We're going to have our 30 over here. And then we're not only just filling in all of this, but we're filling this all the way in here. Okay, so our lower bound is 30. What do we put in for our upper? 1E99, yeah?
Yes.
Okay, and then our average is 34. And we figured out our standard deviation is 1.5. Okay, so those are the 4 things that you're going to type in the calculator to be able to get it. All right. For the last one, this is stuff that we talked about last chapter. When we're given a percentile, what do we have to use to find that one? We got to use the inverse norm button. Okay, and that's only when you have that 95th percentile there. So if you go in there, okay, what we have to find out here, or what we have to plug in, we got to plug in our area, our average, and our standard deviation. Well, we have the average, which is 34. We have the standard deviation of 1.5. Our area is going to be what? 0.95. Yeah. So we plug in all of those. What do we get for an answer? Okay. 36.47. Do we have a label on this one? Yes. 36.47 years. Okay, that's good. Why is it only 2 above the mean? What does the 95th percentile work out to be? 2 standard deviations, right? Okay, so why isn't it exactly 2 standard deviations above? Because of our sample size. Our sample size is going to change that stuff. That's 68, 95, and 99.7. That is just based on a continuous sample size. Okay, this gets a lot more specific based on that sample size. All right, any questions, people? Okay, so I haven't done, I'll tell you this up front, I have not done all of these problems, but these problems are very similar to what we just did. The wordage is a little bit different. Okay, so work through it. But what will help you guys do a much better job on the next test is not just copying down the answers. Okay, show me your work. Show me what you type into your calculator instead of just writing down the answer. Okay? And that's what I expect you to work on the